This is our last lesson of the year. Yay! All right, we're going to talk more about acids and bases, specifically titration. So one thing that we learned last time with neutralization will be very important here. When you react an Arrhenius acid with an Arrhenius base, what do you always generate? Water and salt, okay? And we're going to use that neutralization concept here and link it to titration. The goal of titration typically is to determine the concentration of a substance. Since we're talking about acids and bases, we'll be trying to determine the concentration of an acid or a base. Titration is a technique you can use. It is very easy and fun to perform. I'm going to show you a little video on it. It explains some key concepts very well. A couple things I disagree with, I'll point them out. And then next week, hopefully we'll have the opportunity to perform the titration in the lab. There are some words here that we do want to make sure are clear, but before we go through them, I'm just going to show you the video. And so here's a short video on titration. She's going to illustrate how to perform a titration. So this long glass tube here is a burette. Here's your stopcock. When the stopcock here is parallel with the bench top, it's closed. And when it's perpendicular with the bench top, then it's open and the liquid will run through.
Used to precisely dispense a measurable volume of titrant into an electrolyte solution in a titration until the end point of the reaction is reached. The right hand is used to swirl the flask, while the left hand controls the stopcock from behind the burette. Rotate the stopcock with your thumb, pointer, and middle fingers. This allows better control for delivering partial drops. Check to see if the burette is clean by rinsing with water and noting any beads on the walls. Make sure the stopcock is closed.
Because if you leave the stopcock open and you pour solution into the burette, what's going to happen? It's going to go straight through and fall on the floor.
Eye level. Use the funnel to add small portions of titrant for rinsing.
Another key word is titrant. So the titrant is what goes into the burette.
Wet all areas of the burette with your titrant by rotating horizontally and drain out through the stopcock. Drain all rinses completely. Repeat this 3 times to ensure all contaminants are out. Fill the burette above the 0 mark with your titrant. Pour with the burette below eye level. Pour slowly so the burette does not overflow. Remove the funnel after filling. Check for bubbles in the burette, especially in the tip. Bubbles will cause significant errors in volume. To remove any bubbles, quickly move the stopcock back and forth. Move the burette 0 mark to eye level to avoid parallax and drain slowly to the 0 mark or below.
And so one of the questions I used to ask on the test, I took it off this year not knowing how many groups would be able to perform the titration, but when you prepare a burette, what you want to do is typically you wash it twice with distilled water as she illustrated, and then you're going to wash it 2 times with your titrant. That's the solution you're going to put in the burette. And then you'll fill up the burette past the 0 mark. The 0 mark would be here. You want to go a little bit past, and then you drain it right to the 0, making sure that you don't have any air bubbles. That will affect your volume, which in turn would affect your molarity, and that very often is a source of error.
Remove any hanging drops from the tip of the burette by touching it to a clean glass surface. Any drops are considered delivered volume. Record the initial volume by using a card with a dark line. This helps darken the meniscus for better reading.
And this is the one area, at least I completely disagree with. When you read a burette, you're going to see the graduations here, and you can read it to the 10th, so you have to guesstimate to the 100th. But that 100th place is either a 0 or a 5, and this came up on an AP exam recently, so you want to be comfortable with that. You can read to the 10th, you record to the 100th. You learned about that with significant digits earlier in the year. So this should have been 1.15.
Read it to 2 decimal places. Add 2 to 3 drops of indicator to your analyte. It is wise to do a rough test.
Now this is your analyte. That's what's in your Erlenmeyer flask or your beaker. That's what'll be underneath your burette. That's what you're going to deliver titrant to. This indicator is phenolphthalein, and the solution did not change color. So is that solution an acid or a base? It's an acid. Phenolphthalein in acid is still colorless. If it were a base, what color would it turn? Pink. And that's the indicator that we're going to use in the lab next week.
Titration to determine the relative volume needed to reach the endpoint. Place the flask under the burette on a white background. The color change will be more noticeable. Adjust the burette so the tip is inside your flask to avoid loss of titrant.
So you're starting to see some pink color here. You have what you're delivering, the titrant, which is base, and when it reacts with the indicator, it turns pink. And if you don't swirl throughout, you get pockets of solutions reacting with one another. Now, when you swirl this, you'll swirl that pink color out until you truly have reached the neutralization or equivalence point, and we'll go over that piece in a few minutes.
Titrant rapidly at first, with constant swirling. As the endpoint approaches, the color...
So again, you're still getting back to clear because you're not at the endpoint. The endpoint will be the color change.
will be more persistent. Slowly drops down to 1 per second.
Now
Touch the tip to the sides of the flask and wash the sides down with water so that all titrant that has been delivered has reacted. Slowly open the stop clock and allow a partial drop to form. A partial drop just covers the tip of the burette. Touch the tip and rinse until the endpoint is reached. The endpoint is noted by a faint color that is persistent for at least 10 seconds, but not permanent. Obtain a final reading.
And again,
the volume titrated is the difference.
This is either going to be 10.20 or 10.25. You wouldn't read it that way.
Between the initial and final reading. The concentration of your anion can now be calculated. Let's review the steps.
So that's how you perform a titration, and that's what we're going to be doing in the lab. There are a couple things she did that we'll do a little differently, but we'll talk about that when we do the lab. We want to go over more of the calculation aspect today, but again, you can see that you're adding one reactant from the burette, that's called the titrant. You add it to the other reactant that's typically in an Erlenmeyer flask, maybe a beaker if you have a pH meter in there, and that's known as the analyte. You'll add it until the color change occurs, and that color change marks the end point. That's when you have equivalent amounts of acid and base, and that's the equivalence point. You'll find that the moles of the acid are equivalent to moles of the base, but it also is going to be based on the stoichiometric coefficient. So it's stoichiometric equivalencies, and I'll point that out when we get there. Again, the end point is what you see because that's the color change. You don't see the equivalence point. And the semantics here can be very important. As the video showed, in acidic solution, phenolphthalein is colorless. Phenolphthalein is an indicator. And in basic solution, the phenolphthalein will turn the solution pink. For example, this is a neutralization reaction. Which of the substances is the salt? Sodium chloride, and that's table salt. So when you add just enough base to react completely with the acid, you've reached the equivalence point, and the moles of acid and base are equivalent. That's where you're going to see the color change. The color change is the end point. Before the equivalence point, not all the acid has reacted, so it's colorless. And then way past the equivalence point, you'll have more base, so it'll be pink. Listed here are the steps on how to calculate either concentration or volume. It's more common to calculate concentration, but I'm going to show you how to do both of these. 4 steps. The first step is to write the balanced equation, and for your purposes this year, you're going to get something very simple. You're going to get an Arrhenius acid reacting with an Arrhenius base to generate salt and water. Then you're going to calculate the number of moles or millimoles of acid or base. And it's going to be very obvious which one you're going to calculate initially, because it'll be the one that you have both the molarity and the volume. And just to review for a minute, you will recall, as we talked about in this chapter as well as in the solution chapter, that molarity is equal to moles of solute over the volume in liters. You also can say for example, same formula, I'm going to modify it here. That molarity is equal to millimoles of solute over the volume in mils, because the milli would cancel in each case. Very often, you're going to be given volumes that are in mils. And rather than make conversions all over the place, it's going to be much easier to leave it that way. And using this formula right here, you can calculate millimoles of solute equal to the molarity times the volume in mils. And that will be how you calculate the millimoles of the acid or the base. Whatever you know both the concentration in molarity and the volume of is what you'll find millimoles of first, simply by multiplying those quantities together. Then you can calculate moles or millimoles, just be consistent, of the other substance using the balanced chemical equation. You can do a very simple mole to mole or millimole to millimole conversion. Finally, you'll calculate the concentration or volume, and I'll point that out as we go. We're going to walk through a series of problems. If you follow the steps listed here, which you'll keep in front of you, I think you'll find this to be very, very simple. I'll label the steps as I go so that you can follow them when you look this over and practice additional problems. You don't have to label them unless you feel it's very helpful to you. So in this first problem, it says, in a titration of a sample of 20 mils of hydrochloric acid, 30 mils of 0.2 molar sodium hydroxide, the base, is required for neutralization. Again, it's a neutralization reaction because you react an Arrhenius acid with an Arrhenius base, you generate a salt and water. You're going to neutralize all of the other components, so you won't have acidic or basic nature. You're going to calculate the concentration of the acid at the equivalence point. And at the equivalence point, millimoles of acid is equal to millimoles of base stoichiometrically. So when I get these problems, the first thing I do is I write my balanced chemical equation. And this one's very, very simple. And this is why we learned about neutralization reactions last time. So in this first problem, you're reacting hydrochloric acid with sodium hydroxide. You're going to generate sodium chloride and what? Water. And this one's very simple because you have stoichiometric coefficients of all ones. Then I like to write down the information about the acid and base directly under it. We're looking for the concentration of hydrochloric acid. The volume that's given is 20 mils. The concentration of the sodium hydroxide is 0.2 molar. The volume is 30 mils. So in step A, it says write the balanced equation, and that's what I did right there. And I also like to write the information about each substance directly under it. I find it to be much easier. Then it says calculate the number of moles or millimoles of acid or base. You'll calculate it for the one that you know both the molarity, that is concentration, and volume. So what should we calculate millimoles of, the acid or the base first? Has to be the base because that's the one we know both the concentration and the volume of. So millimoles of sodium hydroxide is equal to the molarity times the volume in mils, as we stated right up above. So we have 0.2 molar times 30 mils. And so that's going to be 2 times 3 is 6. So that's 6 millimoles of sodium hydroxide. Now in step C, we're going to go from millimoles of sodium hydroxide to millimoles of hydrochloric acid. And this one, as I said, is very, very easy because it's a 1-to-1 mole ratio. So 1 millimole of sodium hydroxide is equal to 1 millimole of hydrochloric acid, and that's equal to 6 millimoles of HCl. So now we know millimoles of hydrochloric acid. So in the first step, we wrote the balanced equation with the information below it. In the second step, we calculated the millimoles of the base because we knew both the concentration and the volume, and we established that millimoles can be calculated by multiplying the molarity times the volume. Once we have the millimoles of the base, we can do very simple stoichiometry, a mole to mole or millimole to millimole ratio, and we can calculate the millimoles of hydrochloric acid. And then finally, in the last step, we can calculate the concentration of the acid. We know that that's millimoles of substance. And be careful here, it's just the volume of the acid. You don't add the volumes together here. Be careful, that's a common mistake. And so what was the volume of the acid? 20. And that's the beauty of writing everything underneath it. It's in a nice little package. it's easy to find, and it really makes life much more straightforward. And that's going to be 0.300 molar hydrochloric acid. That's your concentration. So again, in the last step, once you have the millimoles of the acid, you'll divide by the volume to get the concentration. So it's a 4-step process. The only thing you can tweak a little bit is very often you don't have a 1-to-1 mole ratio. I'll give you an example when you don't, and I'm more likely to give you one that doesn't have a 1-to-1 mole ratio on a test because this is too easy. Also, the only other thing you can do is instead of the concentration, you could ask for the volume. So if you were given the concentration and asked for the volume, you would just interchange these two quantities, and I'll give you an example of that as well. Questions on this first titration problem? So again, what might look very, very challenging is really pretty easy if you follow these steps. You'll be very successful here. And you will have a big problem like this on your test. It also will tie in to theoretical yield of the salt as well as percent yield. And I'll do a couple of those at the end, and there are several of them in your classwork. So be very careful there. That ties back to stoichiometry, which we covered at the beginning of the third 9 weeks. Questions here? All right, I'm going to have you talk me through the next one to make sure that you're understanding. In this next problem, which is on the screen, it says in a titration of a sample of 1.5 molar calcium hydroxide, is that the base or the acid? Oh gosh, base, hydroxide base. 25 mils of 0.8 molar hydrobromic acid is required for neutralization. Also, if you can't name acids and bases, or you can't formula write them, you're going to run into a problem. We want to calculate the volume of the base at the equivalence point. So again, what is our first step? We're going to write out a balanced equation. This is a neutralization reaction, and neutralization reactions are double replacement reactions. So that's review also from the very beginning of the third 9 weeks. I usually write acid then base. It really doesn't matter. It's just how I was trained 100 years ago, so why not? Hydrobromic acid. How did I know this was a binary acid? It started with hydro. Reacts with calcium hydroxide. And again, those group 2 bases, don't drop those parentheses. You will crash and burn. If you don't formula write properly, you're probably not going to be able to balance it. So if you can't balance it, Nasser, what does that indicate? You probably...
you won't get the right stoichiometric coefficient.
Well, you won't get the right stoichiometric coefficients, but it probably indicates what about your formula writing? It's wrong. All right? What are you going to generate? Jason, what's the salt? Sam, help him out. That's correct. Where'd you get the 2 from? Calcium's in group 2, so it has a 2+ charge, which drops. And what's always your other product, Jason? about it, Cameron? Water is correct. Alrighty! Next thing you want to do is balance that equation. We talked about neutralization reactions in great detail yesterday. In the event you had poor focus or just need to review, the video is posted. Balanced equation, let's get the information. The concentration of the base is 1.50 molar. We want to know the volume of the base at the equivalence point where millimoles of acid and base are stoichiometrically equivalent. In regard to the acid, the concentration is provided at 0.8 molar. I'm having a pen problem. And what's the volume of the acid? Good, 25 mils. Alrighty, what do I do next? Michael?
You multiply the 0.8. Yeah, you multiply the 0.800 molarity times the volume.
Why do you do that?
To calculate the millimoles.
To calculate millimoles of what?
Hydrobromic acid.
You got it. So to get millimoles of hydrobromic acid, you're going to multiply the molarity times the volume. And that's 20 millimoles of hydrobromic acid. And what are you going to do with that 20 millimoles of hydrobromic acid? I probably wouldn't start a new line, but I just wanted you to see the individual steps. Go ahead, Sam.
The millimole fraction, and it would be 2 moles of hydrobromic acid, and then 1 mole of calcium hydroxide. 1 millimole.
Yeah, and just to keep consistent, but not the hugest deal. So that would be how many millimoles of calcium hydroxide? Correct. All right, and then the only way this one's different from the other one is we're asked for the volume of calcium hydroxide. And again, if you go back to your original formula here, and some of you have mastered this concept, some of you are a little cockeyed with it, you can interchange a numerator and a denominator on opposite sides of an equation. So volume is equal to millimoles of the solute over the concentration and molarity. I'll show you how the units cancel here. So what you've got then is you've got 10 millimoles of calcium hydroxide, and you're going to divide that by the concentration that was given. Now it's capital M. I'm going to do millimoles over milliliters so you can see that the millimoles cancel. You have milliliters in the denominator of a denominator. That's like 1 over 1 mil. So that's mils. And I can show you that fraction more clearly if you're struggling to see it. 10 divided by 1.5 is 6.67 mils of base. And be careful with this stoichiometric equivalency. Again, These are stoichiometrically equivalent, but the millimole quantity may not be the same, and it won't be if you don't have a 1-to-1 mole ratio of acid to base. So be careful there. What is nice is if you wanted to know the yield of salt or the yield of water even, you could use either of these to drive it since they're stoichiometrically equivalent. And I'll point that out in the next one.
Can you go back up to the top one?
Just to get the volume aspect? Yeah. All right, so you can calculate concentration or you can calculate volume. The third problem is a little bit different looking. I'll help you write the balanced equation. Probably wouldn't give you this type of equation on the test because it could introduce some ambiguity, and I don't want the equation to be an issue for you. But it's really a nice question, and it also mentions something that is important. It's important that you understand how chemistry affects your lives. Hopefully you got some of that in the project I gave you first semester. And we try and link chemistry to relevant goings on in the world. But this is something that maybe you do or don't know, but something you can easily understand at this point. It says, in a titration of a sample of vinegar, 11.10 mils of 0.748 molar strontium hydroxide, is that the acid or the base? The base. Is required to neutralize 10 mils of vinegar. It says calculate the concentration of acetic acid in this sample of vinegar at the equivalence point. So what you want to know is the concentration of acetic acid, and I wouldn't necessarily give you that chemical formula. You should be able to write acetic acid out. What is interesting here, and for those of you who go on to do like SAT 2 Chem, they ask a lot of relevant chemistry questions in that they would expect that you knew that vinegar contains acetic acid. And that's why I like to give these types of problems where they're a little more relevant to what you do. You also can put vinegar down your garbage disposal, and it really gets rid of bad odor. It reacts with whatever's in there, and it helps with the stench. In any event, this problem has multiple parts. It asks for the concentration of acetic acid. I believe you had this in your notes, which we're going to do, and then I don't think I had given you this. I assumed you remembered it, but I want to make sure you remember it because it's something that I taught you earlier and I assessed you on the test on, and it's all over your classwork. So I thought it would be good to do a practice problem there. In any event, let's get the balanced equation down and make sure you can work through this. On number 3, you've got acetic acid reacting with strontium hydroxide. Now acetic acid is a little bit funky. The ionizable proton is the H off the Cu group. We went over that with the conjugates initially. What you generate is strontium acetate. That should be a parenthesis. No, the H comes off. The H is going to hook up with these. I started to make a parenthesis. I made a mess. And water. And then just watch your balancing here. Sometimes the kids get a little bit confused here. And again, I'm probably going to give you a much simpler acid, but I just wanted to go over this. I actually have 2 titration labs. One deals with vinegar. The other is a sulfuric acid sodium hydroxide titration. in any event, the concentration of strontium hydroxide is given at 0.748 molar. The volume is 11.10 mils. The volume of the vinegar is 10 mils. And we want to know the concentration of the acid. So what am I going to get millimoles of first? Why would it not be acetic acid? Because you are not given the concentration. So you're going to go after the millimoles of strontium hydroxide first by multiplying the concentration and the volume. And again, do millimoles because you don't have to do conversions. It really makes it easier. So that's going to be 8.30 millimoles of strontium hydroxide. And, you know, titration, if you follow the steps, is pretty regimented. You still need to be able to think, but more importantly, or also as additionally important, you've got to do a lot of practice problems to be successful. From this, what am I going to do? I need to get to what? You got it. You need to get to millimoles of acetic acid. And from the balanced equation, for every 1 mole of the base, I've got 2, and I guess you would do milli because that's what you have there, 2 millimoles of acetic acid. So that's going to be 16.6. And then if you want to know the concentration of the acetic acid, you're going to have 16.6 millimoles of it, and you're going to divide that by what? Huh? 10. I don't know why I did that. Yeah, that I don't know what possessed me to do that. So 1.66, I'm like, where did that come from? Silly, silly. Sorry. 1.66 molar. And you'll get a lot of practice calculating concentrations of acid or base by titration. The other thing I do want to mention here with you is this next question says calculate the theoretical yield of the salt. Now remember, if you're going after a yield, you have to go after a reactant or a product. Products get yielded. And you have 2 options. You can either use millimoles of the base or millimoles of the acid. I would use the one that I calculated first, because if you made a balancing error, you're going to follow that error through. So I would go back to the millimoles of the base, and then I would calculate the mass of the salt in grams. Now you can use millimoles of the acid. They're stoichiometrically the same, so it doesn't matter which you start with. The only thing I will say is that get yourself to moles and again, you know that 1 mole is 10 to the third millimoles. So when you divide this by 1,000, you either move the decimal 3 to the left or simply multiply by 10 to the negative third. From here, in 2 steps, you can get to the mass of the salt. So in the first step, what you're going to do from the balanced equation, you have 1 mole of the base and 1 mole of that salt. And then you have 1 mole of the salt, and I'll put that up above because you won't be able to see it otherwise. And then the mass in grams. So you've got a strontium and you're going to multiply that by the moles. It's a lot of steps. And you've got 1.71 grams of strontium acetate. And there's nothing new here from what you already know how to do. It's just a matter of remembering how to do theoretical yield from way back when. So again, you can start with the moles of the acid or the base. It doesn't matter which. And in 2 steps, you're going to do your stoichiometry to get to the mass of the salt. The next question says that the percent yield is 80. And we want to know the actual yield. You may or may not recall that percent yield is equal to actual yield over theoretical yield times 100. So if you want to know the actual yield, you're going to do the percent yield over 100 times the theoretical yield. So the percent yield over 100 is 0.8 times 1.71 grams. And that's 1.37 grams. And this is in your stoichiometry chapter, and quiz 3.2 had some good practice problems here. You'll also find more of these older types of problems in your classwork. Before we break, I just want to mention one thing. In your notes, it reviews strong acids and bases. There's nothing here that I haven't mentioned to you already. A strong acid ionizes completely. A strong base ionizes completely. It also reviews the strong acids, polyprotic, etc. So we already did this section. You can read back through it. One more minute of your time, please. The acid-base equilibria with Ka, Kb, and Kw, you will not be responsible for, so don't worry about it. And that ends our chapter. There is a question in the back. Go ahead. Okay. Questions in regard to your lesson. That 3-step process to calculate the concentration of an acid or a base, that 4-step process will be very, very helpful to you. You can now complete all of your classwork, which is what you're going to be working on in class tomorrow. If you're not going to be here tomorrow, make sure you bring your stuff home. You want all of that classwork done by Tuesday, so you can complete all of it. Now be aware in regard to your classwork, there are titration problems on both classwork sheets. So on classwork 4.4, you're going to find that the back has some titration problems. You want to make sure you're comfortable doing those. Those are questions 29, 30, and 31. 31 has some questions on theoretical yield and percent yield like I just did, so that would be good to do. Your test question looks a lot like 31. On the back of your acid and base naming sheet, there also is a good titration type problem, and that will be very good practice for your test as well. So I highly recommend that you are extremely productive in class tomorrow. You have a full period just to practice. Other questions in regard to the lesson? All right, so that's our last piece of acid and base. We've talked about titration, naming, neutralization, pH, proton concentration, POH, hydroxide concentration, properties, as well as definitions for acids and bases. Your quiz covers definitions of acids and bases, properties of acids and bases. The biggest emphasis on your quiz, you've got conjugates, you've got to identify those, predict products of Bronsted-Lowry acid-base reactions, but your big focus on the quiz is pH, proton, hydroxide ion, POH, concentration of strong acid. That's the big crux of your quiz. Okay?